This is the formula. We have e to the j times 0 degree equals to cosine of 0 plus j times sine of 0. And that is 1. So no big deal here. Nothing new. Which means we are considering the unit complex number on the real axis. Okay, so that's the case number 1. For case number 2, when r is 1 again, but theta equals pi. So when r equals 1, theta equals pi, the angle is pi, or the argument is pi. Where is the complex number? 0 degree, 90 degree, 180 degree pi, right? So it's here. This is negative. So this is E0. And this is e to the j times pi. So what happened here? If you look at the Euler's formula, you have e to the j times pi equals cosine of pi plus j times sine of pi. Am I right? Okay, so I think last time we were here, right? Okay? So what is cosine of pi? Cosine of pi equals to negative, right? Okay, minus 1. And j times sine of pi, what is sine of pi? 0, good. So it's here. It is here. Now, so what is the big deal here? What can I say over here? If you look at the result, let me move negative 1 to the left-hand side. I have e to the j times pi plus 1 equals 0. And we call this the king of the equation. The king of the equation. How come it is the king of the equation? That means it is the most important one. Why? Because if you look at this equation, it involves the natural number. It involves j, the square root of negative. It involves pi, the pi. Okay, it involves 1, the unit number of the multiplication. It involves 0, the unit number of addition. It involves the operation plus addition. Okay, so all the basic stuff in mathematics now are involved in this small equation. So that's why we call this the king of the equation. It all comes from Euler's formula. Okay, now due to the time limitation, I cannot prove. This is true. Okay, e to the j. So let me repeat that here. I did not prove it. I just show you directly. It can be proved mathematically or geometrically. You say that the magnitude of this guy, e to the j theta, is 1. So it has unity there. Good. Thank you. Appreciate it. suppose this is the unit circle. So the magnitude is 1. Okay, and then we have e to the j theta over here. And the angle between this complex number e to the j theta to the positive real axis is theta. Okay? So you can see that the real number projection onto the real axis is given by cosine of theta. The imaginary part is simply sine of theta, right? Okay? Again, this can be proved, but due to the time limitation, I did not prove it for you. Okay? You can find a proof in many fundamental calculus book. Any questions up to this moment? So you can write it this way. The magnitude is 1. Okay, now let's look at some operations on the complex numbers very quickly. Now, since this is not a course on mathematics, so I can only give you a very brief review. Okay? In case you have any question, please raise your hand and let me know. All right? Okay? No? Okay. Okay, let's assume I have two complex numbers. D1 equals x1 plus j times y1. And D2 equals to that x2 plus j times y2. So now we have two complex numbers. Z1 plus x1 plus j times y1 is z1. x2 plus j times y2, that's z2. So the complex pair and z1 here. And I have another complex number, so z2 here. Alright, so the first operation is d1 plus d2. Okay, so we have x1 j times y1 plus x2 plus j times y2. Now, since the real part and the imaginary part are independent, so the sum of the two complex numbers is simply the sum of the real part plus j times the sum of the imaginary part. Okay, likewise, subtraction. Subtraction. So by this definition, or this operation, you can treat it as a definition. You will see that you can treat the complex number just like a two-dimensional vector. Okay, so the sum of z1 and z2 is simply this vector z1 plus the vector z2. So this is z1 plus z2. Right? Okay, so they can be treated like a two-dimensional vector. Okay? And similarly for z1 minus z2. So we have z1 minus z2. So z1 relative to z2. This guy Z to Z2. So treat them like vectors. And this one is simply Z1 plus Z2. The vector sum of Z1 and Z2. Okay? So the subtraction and addition are pretty much the same as the two-dimensional vectors. So they can be treated as two-dimensional vectors. Okay, 2D vectors. All right, so that's the subtraction and addition. What about the multiplication? Okay, so let me bring that up here. So I have Z1. And the Z2. Now, if you and me try to perform the production, Z1 times Z2, well, one way to do it is to use the standard definition and expand the product. Okay, so you have eventually you have x1, f2 minus, oops, sorry, y1 times y2 plus j times x1, y2 plus x2, y1. That's a standard product of numbers, right? But this does not give us the intuition, insight very clear. So we prefer to write in so-called Euler form, or by using the Euler's formula. So this can be written as, say, R1 times e to the J1. And this can be written as R2 times e to the J2. So in this case, the R1, so R1 is the square root. Okay, and the theta 1. This is actually for the root. So, you write the maybe let me use the spatial. One more time, this means it is a complex pen. Okay, G means it's a complex pen. So this is the real axis, and this is the imaginary axis. So the Z1. Okay, and also we have a D2. The angle is theta 2, the distance or the magnitude is R2. Okay, so far so good. So once I use the polar form or using the Euler's formula, the product can be written as R times e to the J R1, R2 times e to the J theta 2. Right? Okay? So now I have So now let's combine the magnitude with magnitude. And e to the j theta 1 with e to the j theta 2. So R1 times R2 times e to the j theta 1 plus, this one, not plus, times e to the j theta 2. Okay, so R1 times R2, that is the magnitude. Okay. What about the product of these two exponentials, e to the j theta 1 and e to the j theta 2? What's that? The product of these two exponential numbers becomes what? And I simplify the notation. E to the j times what? Theta 1 plus theta 2, yes. Great. Okay? So now the product can be found much more easily. Much more easily. So I have theta 1 and theta 2. So the product has theta 1 plus theta 2. So that will be somewhere over here, probably. So this is the theta 1 plus theta 2. So the argument or the angle is simply the sum of theta 1 and theta 2. And what about the magnitude or distance? So this is d1 times d2. Okay, so the magnitude is simply a product of R1 times R2. Right? So this makes the product much more easier to perform, to obtain the result. Okay? Got it? Any question up to this moment? Any question? Gentlemen, do you have a notebook? Yeah. No. Please use a paper notebook, physical notebook. Okay? Could you now next time down? Come on. We have plenty of time here. Okay? Because if you use an iPad or something like that, I don't think it's very convenient. Buy a notebook and come back ASAP, please. Okay, that's a product. Similarly, what about division? Z1 over Z2, sorry. Can anyone tell me how to do this from your high school math? You have the division of the ratio of two complex numbers. How do you compute the ratio or the division? Usually, how should we do here? We multiply what? X2 minus j times y2, right? In order to make the denominator a real number. That's the way we did. We learned from the high school, right? So this becomes x2 squared plus y2 squared in the denominator. And the product of the numerator is simply x1, x2 plus y1, y2 plus j times x1, y2. Okay? And minus y1. That's the way we learn from high school. We try to make the denominator a real number first. Okay? And you can can simplify this expression from here. Okay, or we can use this technique we have learned just a couple minutes ago. Okay, or so that's equal to R1 over R2. So that's a magnitude of the ratio of the complex number Z1 and Z2. Times into the J times what? What is the exponent here? J times Z1 minus Z2, good, yes. So on the complex plan, the ratio of Z1 and Z2 becomes very easy to represent or to draw or to sketch. Okay, so we have R1 minus Z1 minus Z2. So this is Z1, this is Z2, sorry. So that will be negative. It will be negative. So this is Z1 minus Z2. It's a negative number from the previous vehicle. And then the magnitude is simply the ratio R1 over R2. Okay? So it's easy to compute, right? Yes.
The second line is J x2 y minus x1.
Oh, let me check. Okay, I mean, maybe. Y1 times y, x1 minus y2. And J y1 times x2. Oh. Should be plus. And negative. Sorry. Thank you. Thank you. Sorry, can you? Oh. You mean this one? Okay. Okay. So this is x2 times x2 first, right? Okay, and then we have, let's consider another real number plus y2 times y2. Okay, and then j times y2 x2, and then minus x2 times y2. Right? Okay? So actually this is the magnitude square of Z2. So this equals to, sorry, square. This is 0. Okay? Right. Good. Any other question? If you have any question, raise your hand to stop me. Okay? So that I can give you some explanation. In case I also may make a mistake, so that happens sometimes. Sorry about that. Any other question? Okay? Alright, so why do we need this? Before we move on, why do we need this? Because we are going to look at another important stuff called phasor. Okay, before we move on, any other question about this? Any question? Some of you may come from I think it's come from the Department of Electrical Engineering, right? So the further stuff is going to be the one you are familiar with, okay, the phasor. Okay, so I'm going to go. Okay, before we look at the phasor, there are some stuff. If you look at the lecture notes, okay, all those identity for sin theta equals to 1 e to j theta plus e to the negative j theta. And sine theta equals to the imaginary part of e to the j theta, and also equals to 1/2 times j times e to the j theta minus e to the negative j theta. And also some other examples here. Again, since we have very limited time, so I won't be able to go through every details, okay? So I need to ask you to look at the stuff, those material by yourself. And in case you have any question or problem, let me know, all right? Okay? Because I think these are very intuitive and also very simple. Okay, now here we have a signal. It's a sinusoidal signal. Okay, let me turn off the light first. Oops, not this one. What's the switch? Oops. All right, now this is either a sinusoidal signal A times cosine of omega sub 0 times t plus psi. Now this omega sub 0 is called the frequency of the signal, and the psi is called the phase angle. Okay? Now, actually this is not the only way to introduce the signal. So let me use a spatial. Okay, some people use cosine, but sometimes occasionally I prefer to use sine. Okay, there's a reason for that. Now, let me show you one interesting figure over here. Suppose I can rewrite, okay, maybe stop with this. This one first. Now this can be written as the sine as the imaginary part of let's start from this one first. Okay, like I just tell you. This number, okay, in this case, can be written as imaginary part of A times e to the j times omega sub 0 plus times t plus psi. Okay, maybe give you one stuff here. And A times cosine omega sub 0 sine. Okay, so now I express the e to the j omega sub 0 times t plus psi as the sum of cosine and the sine function by using the Euler's formula. Okay? Now for the moment, let's assume that A is a real number, just for the moment. Okay? Make that easier, right? So geometrically or physically, how do I get this sketch, this signal? Okay, this is the. Sorry, let me change my mind. Maybe I start with sine. I have a bigger right there, so let me use sine first. Sorry about this. about the imaginary that this will be imaginary part. Good. Sorry. Okay, so I change this to sine. Sorry about this. So for the moment, we can let A be L, positive real number, positive real number. Okay? Make that easier. This is sine. So if you look at the imaginary part, that gives A times sine of omega sub 0 times t plus sine. Okay? Got it? Any question up to this moment? Because if I expand this exponential number, this can be written as cosine of omega sub 0 times t plus sine and plus sine times sine of omega sub 0. Sorry, this is the type. Omega sub 0 times t plus sine, right? Okay? All right, so now I have a figure to show you. I like this part, and this is very simple but very interesting. Okay, now the radius of this circle is supposed to be A. Okay. So this is A, the magnitude or the radius of the circle. Now let's assume when t is 0, okay, let me put this here. So as t equals 0, theta is equal to theta equals to sine, right? Okay? So initially, here I have the circle. And the radius of the circle is A. And here we have a time basis of omega sub 0. Now this time basis is multiplied by the frequency omega sub 0 times 3. Now initially if I stop here, this is sine, so I can map or project this point. Axis. And this is the sine of sine. Okay? Now if we increase the time, you can see that this complex number, this entire complex number of this one, is going to rotate. Okay? So next time we move to here. Presumably here. So I have this one. not known here. So that's why it's called a base angle. Now, since this angle is bigger than 0, so make this base lead or base leg. This is a base lead or base leg. Base lead. Yeah, good. This is a base lead angle. Okay? Now, if I have another similar one, maybe take a break now. Okay, let's take